Hello, and welcome to today's video of semiconductor materials, where today we will be covering diffusion coefficient. In a previous video, we discussed diffusion current. Today, we'll be taking it a step further and looking at diffusion coefficient. We can note that diffusion coefficient is denoted as D, and it is equal to D naught times E to the power of negative Q divided by R times T. Where D naught is the proportionality constant, we have Q, which is our activation energy, R, which is our gas constant, which is 8.314, and T, which is absolute temperature. For our last variable T, it is important to note that we should deal with temperature in Kelvin. This is to simplify our equation since our gas constant is also given in kelvins. Let's go ahead and look at an example to further understand. Our example states that for a semiconductor device containing gold and silicon, the diffusion coefficient at 1 degree Celsius is 0.0658 meters squared times seconds to the negative 1 power. Calculate the activation energy if the temperature is raised to 35 degrees Celsius and diffusion coefficient lowers to 0.1818 meters squared times s to the negative 1 power. We can start off by noting what the problem is asking, which is to calculate for the activation energy, also known as the variable Q. Since we have two diffusion coefficients at two different temperatures, we can go ahead and write out our formulas for both using only variables to start. So we can say that D1 is equal to 0.0658, which is at temperature 1 degrees Celsius, and we can add 273 to convert this to Kelvin. So we have 274 kelvins as our temperature. For our second diffusion coefficient, we have 0.1818, which is at temperature 35 degrees Celsius, and again adding 273 to convert to Kelvin, so that gives us 308 Kelvin. And now that we know our variables, we can go ahead and set up our equation for diffusion coefficient. So we can write D1 is equal to D naught times e to the negative q divided by r times T1, and for our second diffusion coefficient, it is equal to D naught times e to the negative q divided by r times T2. Now that we have two equations, we need to use both of these to solve for Q, our activation energy. We can do so by dividing. So we can write D1 divided by D2 is equal to D naught times e to negative q divided by RT1. And we can divide this by D naught e to the negative q divided by r times T2. Let's go ahead and wipe the board to continue to solve. Our next step is to simplify, since we have our main division and we have our powers that are being divided as well. We can start off by canceling D naught and writing e to the negative q divided by r times 1 over T1 minus 1 over T2. Our next step in simplifying is to get rid of this exponential and taking the natural log on both sides. So we have the natural log of D1, D2, and when we take the natural log of our exponential, it cancels out. So we have negative q divided by r, and we have 1 over T1 minus 1 over T2. Let's go ahead and wipe the board again to continue to solve. So our next step in solving is to move our activation variable Q to the left-hand side. We can do this by dividing first our temperature. So we have the natural log of d1 over d2 divided by 1 over T1 minus 1 over T2, which is equal to negative Q divided by R. And so now we can multiply R to single out our variable Q. So we have the natural log of D1 divided by D2 divided by 1 over T1 minus 1 over T2 times R is equal to negative Q. And so I'm going to wipe the board again to continue to solve. And so we can go ahead and switch our Q to the left-hand side and all of our left-hand side to the right-hand side. And so we keep our negative on the right-hand side, and we have the natural log of D1 D2 times R all over 1 over T1 minus 1 over T2. And to make this easier to read, I'm going to go ahead and just clear the board so we only have our final equation. So now that we set up our equation, we can go ahead and start plugging in our values. So we have Q is equal to the negative natural log of D1, which is 0.0658, divided by D2, which is 0.1818, times R, which is our gas constant, 8.314, and we can divide this by 1 over T1 in Kelvin, which is 274, minus 1 over T2, which is 308 Kelvin. And after inputting this into our calculator, we have 209.72.44 joules over mole as our final answer. This concludes our video on diffusion coefficient. Thank you for watching.